Limits are one of the most fundamental ideas in calculus. They help us understand function behavior even in situations where direct evaluation isn't possible. But what does that really mean? I'm Mauro, and we're talking about limits and how they build the foundations for more advanced calculus topics. Let's take a look at the function we have graphed. F of x equals x squared minus 4. If we want to know the exact value of the graph when x is equal to 2, we simply have to plug 2 in for our x value to see that it is equal to 0. As we can see from our graph, at x equals 2, the graph crosses the y-axis. But what if we don't plug x equals 2 in directly? What if instead we check values that are increasingly close to 2 but never quite reach 2? That, in essence, is what our limit does for us. It tells us what a function does as x moves towards a certain value. Here I've plugged a few values into our function, some of which are approaching 2 from numbers less than 2, and some of which are approaching 2 from numbers greater. As you can see, as our digits get closer, and in fact we'll see later on as they get infinitely closer to 2, the function is approaching 0 from both sides. This is what we would call a two-sided limit, or simply a limit. For a limit to exist, it must approach the same value from both values greater than our chosen a value and values less than our chosen a value. And in this case, as you can see, our numbers continue to get smaller until eventually they would be nearly equivalent to 2. If we were to write this as a limit, we would write the limit as x approaches 2 of x squared minus 4 is equal to 0. Or more generally, the limit as x approaches a of f of x equals L. As x approaches a, y approaches L. As the graph of the function f of x equals x squared minus 4 approaches x equals 2, the graph continuously approaches 0. But more importantly, the limit tells us where the graph is headed, the direction it's headed in, not necessarily the exact value. So let's talk about finding limits through direct substitution. Here we have the same equation that we were using before, the limit as x approaches 2 of x squared minus 4. Simply, we would take our limit and plug our value in, showing us that even as x gets infinitely close to the value 2, eventually the value will be 0. It's not quite touching 0, but it's infinitely close to it, which in the world of limits is enough for us to have our answer. Let's look at another problem. Find the limit as x approaches 2 of 3x minus 7. Following the same method as before, we directly substitute 2 in to get our value. We can see that for this linear function, our graph is approaching -1. If you'd like, you can graph it out and see for yourself. And for our third example, we have the limit as x approaches 1 of x squared minus 1 divided by x minus 1. When we plug our x in here to evaluate, though, through direct substitution, we find ourselves with a problem. We get division by 0, which even when 0 is in the numerator, we cannot do. This is what is called indeterminate form. Indeterminate form arises when we have division by 0, particularly 0 over 0, when we have infinity forms such as infinity over infinity, infinity minus infinity, or infinity times 0. All of those are indeterminate forms that we unfortunately cannot evaluate through direct substitution. In future videos, though, we'll go over ways to solve them algebraically, and in the future even with calculus. Thank you for watching. If you liked the video, please give it a thumbs up and leave a comment if you have any questions. If you have a math question that you're needing help with, drop it in the comments as well, and I'll do a video on it and see if I can help you out. Thanks for watching.